Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on December 29, 2025, about 2 days ago. It runs a large, controlled benchmark of more than 12 parameter-efficient fine-tuning methods for reinforcement learning with verifiable rewards, and it finds that structural adapters like DORA, Ada LoRa, and misbeat standard LoRa, while some SVD-based initializations can collapse catastrophically. The paper is titled, Evaluating Parameter-Efficient Methods for RLVR. Okay, and the implications for how people pick adapters for reinforcement learning training are quite significant. Figure 1 makes the trade-off really concrete, because it links reasoning accuracy to how many parameters you actually train. The left panel plots average accuracy against trainable parameter percent on a log scale, and the shaded region marks the best efficiency frontier. DORA sits near the top with low trainable fraction, while PISA and MILO-RA drop close to the bottom. The right panel shows accuracy reward over steps, where DORA and full fine-tuning rise steadily, but PISA collapses downward. Figure 2 explains why the comparisons in Figure 1 are meant to be fair, because it lays out the full evaluation recipe. The left block groups parameter-efficient fine-tuning methods into baselines, structural variants, initialization strategies, other parameter-efficient fine-tuning methods, and efficiency-focused methods. The center block fixes the base models, the training dataset, and the math benchmarks. The right block lists the ablations, which are controlled sweeps over RLVR loss type, learning rate, LoRa rank, and batch size. Table 1 is basically a cheat sheet for what each parameter-efficient fine-tuning method changes inside the model, and how training starts for that method. The left column groups methods into baselines, structural variants, initialization strategies, efficiency variants, and other methods. The middle column gives the forward update rule, which is the exact math for how the adapter modifies W0x. The right column lists initialization choices, because starting A and B in different ways can make reinforcement learning stable or brittle. Figure 3 explains why SVD-based adapter initialization can break under reinforcement learning with verifiable rewards, because the updates do not stay where the initialization puts them. The left panel plots update magnitude across principal component index, and MI-LoRa and PISSA spike toward top components instead of spreading out. The center panel shows cumulative energy, where SVD methods concentrate energy in very few components. The right panel shows the payoff, with PISSA collapsing while full fine-tuning keeps rising, and MI-LoRa stalls. Table 3 shows that the choice of adapter can make or break reinforcement learning with verifiable rewards, because some methods simply cannot express the needed policy change. The full table lays out average accuracy plus pass rates across multiple math benchmarks. The highlighted structural methods stand out, with DORA reaching about 47% average. The initialization-based block is the warning sign, PISSA collapses to near zero, and MI-LoRa stays far behind. The key point is that the adapter ranking mostly survives when the model scales up, so these choices are not just small model quirks. Table 6 summarizes results on a 7 billion parameter model across multiple math benchmarks, with both average accuracy and pass scores. DORA and LoRa Plus sit at about 55% average, slightly ahead of standard LoRa. DORA also looks especially strong on AMC, which supports the idea that structure and optimization tweaks matter in RLVR. Alright, 2 takeaways stand out. Structural adapters like DORA tend to beat standard LoRa for reinforcement learning with verifiable rewards, and some SVD-based initializations can collapse badly, so initialization and geometry really matter. More broadly, this pushes the community to treat adapter choice as an optimization design decision, not a default. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.